Hi, I am Muliang from A-Star Singapore. In this video, I'm going to introduce our new work in Open World Object Detection in CVPR 2025. Open World Object Detection aims to detect and continually learn previously unseen objects, which we often refer to as the unknown objects. These unknown objects can be detected via shared visual or functional attributes with the known objects. In order to use attributes to detect unknown objects, we often begin with a large pool of potentially relevant attributes, which are prompted by a large language model. The major challenge lies in effectively refining a subset of highly relevant attributes to enable reliable detection of both known and unknown objects. We model this problem as a partial optimal transport problem, enabling end-to-end attribute selection and optimization for effectively detecting both known and unknown objects. We propose partial attribute assignment, a three-step algorithm that progressively selects and optimizes a targeted subset of relevant attributes throughout the training process in an end-to-end manner. Now we introduce the three steps in detail, respectively. In the first step of partial attribute assignment, we conduct the initial optimization of attribute embeddings by solving the POD problem between visual and attribute embeddings, both coming from a frozen pre-trained vision language model. The solved POD plan T is to be used in the second step. Curriculum attribute selection. In this step, we gradually select a smaller subset of most relevant attributes based on relevance score originated from the POD plan. As the POD plan T manifests the correlation between individual visual and attribute embeddings, we can sum along the column of T to accumulate the relevance of one attribute to each of the visual objects, defining the relevance score. Hence, we can gradually select a smaller subset of most relevant attributes based on the value of S during training. Finally, in the third step, we use the selected attributes to calculate the object class predictions of each visual input. When calculating the class predictions, we use the relevance score S to reweight the selected attributes, which serves as a complementary soft filtering strategy besides the hard selection in the previous step. The attribute embeddings are optimized by the cross-entropy loss and then undergone the next round of the three-step iteration. In experiments, we use 5 real-world object detection datasets. The classes in each dataset are divided into known and unknown classes. The probability of unknown objects is calculated as the task's relevance times unknownness. The task relevance is the probability of one visual input being related to the optimized attribute embeddings, and the unknownness is the probability of the visual input not being from the known classes. For all experiments, we use MAP as the evaluation metric. From experimental results, we can observe significant performance improvement over the existing state-of-the-art methods. Also, we show that our method is able to accurately detect both known and unknown objects with explainable attributes. That's all of my sharing. Thank you for listening.